Quantum mechanics. The name sounds pretty intimidating, and, if we're being honest, the study of quantum mechanics is pretty intimidating and bizarre in itself. The many complex theories on quantum mechanics seemingly convey ideas that not only disobey the physical laws that we attribute to classical mechanics, but also explain the universe in ways that the best physicists struggle to comprehend. In the words of Niels Bohr, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. So let's try and make sense of quantum mechanics and its main theories.
Quantum mechanics is the branch of mechanics that deals with a mathematical description of the motion, interaction, and behavior of matter in relation to energy on the subatomic level. In other words, it's how tiny little particles or waves move and interact with things. Quantum mechanics is governed by theories such as the string theory, or superstring theory, quantum field theory, wave-particle duality, decoherence, superposition, non-locality, and the uncertainty principle. Currently, there are many theories about how these very small particles move and interact with their environment. However, some of them contradict others, and some are so bizarre that it is difficult to get a grip on them. So let's try to make sense of quantum mechanics, starting with superpositions and the wave-particle duality.
To start with, let's look at the wave-particle duality of subatomic particles. Let's first explore this principle of quantum mechanics by exploring what is a wave and what is a particle. An example of wave behavior is sound. To visualize this, let's set up an experiment. Imagine we have a wall with two evenly spaced gaps in it, and in these gaps we have two people standing. Parallel to the wall is a line of people. If the two people in the gaps of the wall shouted, what do you predict would happen? Because sound shows wave-like behavior, all of the people in the line would be able to hear what they shout because they would spread out like so. If sound displayed particle behavior, only the people directly opposite would be able to hear what they shout. So what would happen if the shout displayed wave and particle behavior? To show this, let's get rid of the people standing in the gaps of the walls and place a person further back in line with the center of the wall like this. If this person shouted, what do you think would happen? The answer may be quite difficult to understand. If this person shouted, only certain people would hear it in what is called an inference pattern.
This experiment is called the double slit experiment, but usually uses electrons fired from a certain point. And instead of people who wouldn't even notice when the electrons hit them, there is a detector wall that measures where the electrons hit. In our experiment, this is who would hear it. But how does this work? First, let's imagine this as waves, and once these waves hit the barrier, they will separate into two individual waves, each coming from its own gap in the barrier, like so. This means that the waves can interact with the waves from the other gaps. Once these waves spread out, they will overlap at certain points, known as peaks, and in some parts there will be nothing, known as troughs. When the waves hit the detector wall or the line of people, the peaks will show up as places where the electron hit. This probably isn't making much sense to you, so just for fun, we'll add in what happens when you put little cameras on the other side of the slits.
This shouldn't make a difference, should it? The results were actually quite odd. When the little cameras are turned on, the electrons behave solely like particles, appearing on the detector wall directly in line with the slits, exactly like a particle would. It is as if the wave function of the electron collapses so that it is just a particle. So how can something behave like a particle and a wave at the same time? There are many theories about how this works, such as that they are actually packets made up of particles known as wave packets.
So what do we mean by the term superposition? In the realm of quantum mechanics, if a particle at the subatomic level is in a superposition, it exists across multiple positions, states, and speeds at the same time. Superpositions are as a result of the wave-particle duality, which we explained earlier. If you think of this superposition of subatomic particle waves in terms of only particles, that would mean these particles being in two or more places at once. Let's imagine this as having one ball that is both to the left of you and to the right of you. So why does this happen? How can this happen? It all comes back to the wave-particle nature of the very small. As we explained earlier, particles sometimes behave like waves, in that they extend over some region of space, rather than confined to a certain point. This means that if waves also behave like particles, the particles can be in many places at once. However, these particles don't stay in this superposition forever. Eventually, what is called the wave function must collapse into just one of the possibilities. The wave function is basically a description of where a quantum object is and what it is doing. To simplify this, we'll look at this in terms of only position, and we'll go back to the double slit experiment we talked about previously.
In the double slit experiment, we saw an interference pattern appear on the detector wall. We also noted that more electrons hit on the lines closest to the center. This means that if we repeated the experiment, there would be a high possibility that the electron would fall on the middle line and a relatively low possibility of landing on the outer lines. So where will the electron hit? Let's look at this on this graph. On the y-axis, we will have the probability of finding the particle in one of the lines, and on the x-axis, we will have the line number. As we said before, it will have a high probability of being in the center lines and lower probability of being in the outer lines. So where is it? Here, and also here. Before we observe its position, it too is in a superposition. Once we observe it, however, the wave function collapses into just one position. This wave function can be described by this equation. Apart from all the weird physics symbols, there is a problem. Many of these numbers are very complex and in some cases imaginary, such as the square root of -1. Other equations can also tell you the exact probability of where the electron will be by putting in the wavelength into Schrodinger's equation. For some of you, this might be getting a bit confusing. So let's look at it in the way Edward Schrodinger did in his thought experiment on superpositions.
Imagine that you put a cat in a box with three things: a speck of a radioactive element, a radioactive detector, and a flask of toxic gas. If you leave this cat in a box for 1 hour, then you observe its state, what will happen? If the atom of the radioactive element had decayed, the detector would have triggered a hammer to fall on the flask of toxic gas and killed the cat. However, this will only happen half of the time. That is, if you repeat the experiment many times, the outcome 50% of the time will be that the cat is dead, and 50% of the time the cat will be alive. So what does this mean the instant before you open the box? Intuitively, you would believe that the cat is either dead or alive, but not both. However, before you open the box, the cat is actually in a superposition, both dead and alive. The act of measuring the outcome or opening the box causes the wave function to collapse into just one of the possibilities, either dead or alive. To confuse you even more, we'll pose this question. As you open the box, you either see the cat as dead or you see the cat as alive. So what causes the wave function of your superposition to collapse? Who or what is observing you? You may be thinking there's a reasonable explanation for this superposition, so how do we know it occurs? If we go back to thinking on the atomic scale, focusing on an atom that is in a superposition of both excited and non-excited, we can see this superposition in action. This is achieved when an electromagnetic wave is sent to the quantum object at the right frequency. This causes the atom to alternate progressively between these excited and non-excited states, and when the state of the atom is measured multiple times and averaged, what is known as Rabi oscillations appear. This is what it looks like. The electrons and molecules are also in superpositions, and if they weren't, we'd have to rethink how the atom works. So how does this relate to our lives and the world we live in? How has this superposition of states been used in technology today? If it weren't possible for electrons to be in superpositions, the computer or device you are using to watch this couldn't exist. But why is this? If we look at a hydrogen atom, we can see that there is a single electron orbiting it. Or is it? In actual fact, the electron is sort of everywhere in space, all at once. However, it has certain probabilities of being in certain regions rather than others. But the possibility that that electron can be in a certain place is never zero. So the electron of a hydrogen atom could statistically be at the other side of the universe. This is a bit different to the standard diagrams you see of atoms, like this one, which is odd because in actual fact the atom looks a bit more like this, with the electron existing all around the atom at once, with a high probability of being in certain places than others.
The superposition of the electrons in atoms means that if two atoms are brought together, the electron doesn't stick to just one atom, but is actually shared between them, sometimes forming a chemical bond. The electron is no longer on atom A or atom B, but atom A and B. This means in a molecule such as water, the electron is shared between all of the atoms, which extends over a large range of space. This is how the flow of electrons works through a material. Either the material is a conductor, insulator, or semiconductor. This understanding of how electrons flow through materials is used to make transistors, which make up a computer chip, which powers your computer. This superposition of states has also been used to see light that does not interact with our eyes or any other device, such as a camera. But we'll save that for another video.
As always, if you enjoyed this video, please like it and leave a comment below. We're a new channel to YouTube and need all the help we can get, so please show your support and share this with your friends.